So in this progression of covering many different security privacy topics in different areas, I want to focus on security and privacy as it applies to machine learning. So how many of you are interested in machine learning? Yeah. It's I guess it's our most popular course. It's a very hot topic these days. How many of you have already taken a machine learning course? Yeah, quite a few. Yeah, so yeah, I understand. You went there first before. Yeah, you know, I get it. The pecking order and all, but but yeah, so it's a super hot topic, and it's very important both in general and the security, privacy, implications of it. So I want to focus on that in this lecture. First of all, just talking about a very basic overview of basic machine learning concepts that we'll need to understand. It'll probably be familiar, certainly, to those of you who have already taken a machine learning course. And then look a little bit at the dark sides. What can go wrong with machine learning if it's misused or misapplied, or if the results are misinterpreted? And then look at some explicit attacks. So what can be, kind of what happens when you bring in an active, intelligent adversary into a machine learning environment? You know, what can happen in that case? And some of the defenses. Okay, so let's dive right in. What is machine learning? Basically, it's what the term says. It's a set of technologies that give computers the ability to learn for some definition of the word learn. So to take a set of examples and be able to internalize them and make predictions about future examples based on data without being explicitly programmed, right? And this is, used for a huge variety of applications, and more and more every day. We won't go over, all of those, but the basic, the basic way this works is you take a bunch of data, and the conventional wisdom is the more data, the better. That's why machine learning startups and companies love data. The more data, the better. You take massive amounts of data, put them through these machine learning systems. There's various algorithms, of course, and then you use the data. You use them to make predictions, and then you incorporate those into a huge variety of applications to try to make good decisions for some definition of good. And so this is becoming increasingly ubiquitous, using machine learning in all kinds of situations. There's tons of articles talking about different use cases for machine learning. In one of them from Forbes, data security was the top application for machine learning. So, what does machine learning have to do with data security? How might you use machine learning in data security? There's actually many ways, but just take a guess based on what we've been talking about. Yeah. Exactly. Yeah. So that's the one of the biggest use cases, trying to take a lot of data about network traffic traces, what's been going on in a corporate network, and dump it into this big machine learning magic box and try to analyze the bejeevers out of the data to detect if anything looks suspicious and focus attention on that. And so so that's one of many potentially, interesting applications of machine learning, and again, there are tons of others, and in practically all of these cases, there's certainly evidence that these techniques can be effective. They can make pretty good predictions a lot of the time, depending on how good the data is and how much data and stuff like that. So. So the value of machine learning is clear, and just to dive further into how this typically works in real settings. first of all, you have to have, you typically have data coming in from the physical domain somehow. For example, this top strip represents kind of the abstract steps, whereas more concrete application use cases are down below, like in automotive or computer vision applications. Data comes out of sensors like cameras, radars, whatever, and then it gets digitized somehow, brought into the system. It typically has to get pre-processed. And then it goes through this big machine learning black box that applies some model and makes predictions and then outputs some analysis. And this can then go back into the physical domain by manifesting in actions or decisions and things like that. Like, in the automotive case, machine learning algorithm says, we're about to hit a cow, slam on the brakes, or something like that. Or we're about to see a traffic sign. So, now again, without trying to replicate a machine learning course, which we absolutely have no time to do, but just to give a high-level taxonomy of some of the major different approaches to machine learning, there's different approaches. For example, supervised machine learning systems where the person who's building the model and building the application kind of helps the thing learn. Humans are involved in labeling data, in directing, supervising the feedback and the development of the model, whereas unsupervised machine learning systems try to just kind of dump in a big bucket of data and see what happens. Or, try to make something interesting. Hope something interesting comes out of it, and sometimes in the right context, interesting things do come out of it. And then there's reinforcement learning, where there's it's not supervised per se, but there's a well-defined decision process or benefit or reward system that the machine learning system tries to evolve to maximize reward for a given cost reward function, right? So, without getting into the details, a machine learning, for example, a supervised learning system takes in a bunch of training data, namely points in an input space, typically high-dimensional input space, and some associated points in an output space, and then some output labels. So in this case, the machine learning model we want to create is going to be a classifier, as a standard assumption. We want to take a bunch of input points, and then the eventual goal will be to classify those. But then the input data we use to create the model already is assumed to be already classified, maybe by humans or maybe by other means. And so we take that training data that has the output labels, the classification vector, classification labels, and then the machine learning black box. Its goal is to basically infer a function x to y that matches the training data, that produces the given outputs y, given input x, and then hopefully generalizes to other produce good outputs y prime for different inputs x prime that are not in the original training data. Now, if the machine learning algorithm did not generalize to other inputs, then it would be useless. It would be what we call as a extreme overfit model, a model that only works on that particular inputs and then does crazy things on any other inputs. Then if machine learning systems always did that or often did that, then we would have to toss them out the door. But the benefit is that they usually generalize somewhat, but there is also a risk of overfitting and doing weird things with different inputs not in the training data. So we'll come back to that. So you can think of, in particular applications, how you would use this. For example, object recognition. You take a big boatload of pictures off the internet. Some of them have cats, some of them have dogs, some of them have houses, and you take some data that maybe people have manually labeled cat, dog, house, or crowdsourced. You've used Amazon Mechanical Turk to get a lot of people to label them cat, dog, or house. And then you dump all the images and the labels into the machine learning algorithm. You try to get it to learn how to classify cat, dog, and house. And reproduce labels. Similar, translation or spam filtering. You're just trying to classify an email message into spam or not spam, right? And so those are the two classes. So does this make sense? So this is supervised in that the labels had to come from somewhere. That somebody somehow had to define the labels, spam or not spam, cat, dog, house, to learn from. Now, unsupervised machine learning, again, is an area that just tries to take, in some sense, raw data with no labels and find interesting things, interesting patterns in it. And those patterns often take the form of clusters of some kind, right? So often the objective of an unsupervised machine learning algorithm is clustering, taking a big space of samples of whatever kind in a high-dimensional space, and just having it figure out, well, these samples, there's a lot of things close together in this space that probably, maybe mean something. Maybe they're related to each other. I don't know how or why they're related, but they're probably related. They're close together. And then there's this other, group over here and this other thing. They can do that without necessarily needing anyone to specify, what one of those categories is. They just say, well, here's some things of interest, and then humans can go look at the output later and go, that cluster is, maybe, or maybe not. So, one of the interesting achievements that Google claimed, for example, in this space, is that they fed a ton of YouTube videos into a deep neural net, which, at least they say, just basically learned out of the blue to identify cats. They never taught it the concept of cats. They never gave it, any data with labels, cat or no cat or anything like that. But it somehow, kind of learned to cluster the YouTube videos in such a way that it could identify, this frame of this video has this thing that's like all of these other things that when humans look at it, yeah, that's the cat cluster. All of those frames have cats, even though the deep neural net probably didn't know what to call it. It was like Adam and Eve. I see a connection here. I don't know what to call it. I have to come up with a name for it, right? So that's really interesting and potentially powerful. And then for that last category, reinforcement learning, where we basically start with the blank model, but then we try to refine it or evolve it in a way that optimizes some reward. We have some kind of reward examples. And this often applies to things like control problems, making robots move in smooth ways, maybe make them balance or run fast or something, or games, which have also caught a lot of attention in the machine learning space. And so, one of the big, not too long ago achievements in this space here was when the AlphaGo system was finally able to beat the human champions at the game of Go, and this was quite an achievement. It came quite a while after the machine learning systems had beaten the grandmasters at chess. Why is it so hard? Because actually Go is combinatorially harder than chess. So the number of legal board states, 10 to the 359, that's a really huge number. I'm not going to try to illustrate how huge that number is, but it's really huge. versus, for example, 10 to the only 123 atoms in the visible universe. And, you know, so it's a really, really huge, complex problem. And so, and they observed that this AlphaGo system basically invented new strategies that hadn't been seen in the history of Go. All the human experts, you know, had never thought of that, basically. And so that's certainly very, very interesting. Now, yeah, so just to kind of bring this back to to say applications of machine learning to security. So we talked about this, that one of that Forbes thinks that the #1 use case for machine learning is data security, for better or worse, or correctly or not. How might we use these different types of machine learning in data security environment? And of course, you can think of multiple different problems. Some of them might be more relevant for some of these types of machine learning versus others. For example, if you have a spam database where people have already labeled spam, things spam or not spam, you might use supervised machine learning algorithm, take the existing spam database, learn on that, and then make it try to predict future spam, right? So that's a good, kind of classic example of a supervised machine learning problem. An unsupervised machine learning problem might be the intrusion detection issue. So you're not sure what you're looking for, but you're just looking for something that looks different from what's normally happening on the network, right? So this is kind of more of a clustering problem. You're looking at, you're just dumping raw traffic patterns in a big unsupervised learning model. And it's doing clustering. It's saying, it's identifying clusters, and then you go look over it and you say, this cluster that it's identified is this particular application. That's Microsoft Exchange traffic from all these, laptops, and this is web traffic, and this is email traffic. I know these clusters. And then you wait, you let it go, and then you wait and see if it ever identifies a new unfamiliar cluster. And then you go, I wonder what that is. Is it just somebody started a new application on the network, something that has a different traffic pattern than the existing known traffic patterns? Or is it, malware activity? Somebody broke in and is doing something different. So it can be a warning system, right? And then, I won't. So those are just a couple examples anyway. Now, again, machine learning is a huge and diverse topic. There's a large number of different approaches to machine learning. Here's one of the many kind of graph, taxonomies of the many different types of algorithms. So, I definitely won't try to get into all of those. But just one of the core, very common classic architectures is what we call a neural network, which basically is a multi-tier processing system where the input data comes in, and then it goes through a series of virtual neurons that each of which takes some inputs, does some transformation, some basic, very simple calculation based on it, and then produces some outputs that it produces real numbered output, either integer or real numbered outputs. It fires or doesn't fire, or it produces a level from 0 to 1, excitement level or something like that. And then the next layer takes the previous layer's inputs, does more of the same simple kind of computation, and then you continue that for some number of stages, and then finally produce outputs. So so again, without getting into the details, that's kind of the basic structure of a classic neural net. So you've probably heard the term, deep neural networks. This is one class of modern machine learning algorithms. What's the difference between a deep neural net and a regular neural net? Well, I mean, there's a lot of details to argue about, but basically they're just talking about adding a lot more depth. So adding a lot more stages, putting this through many more layers. And if you have a ton of data and a ton of resources like a company like Google has, you can afford to throw a lot of hardware at this and a lot of processing power, and it's turns out to be really impressive what you can do. So one of the examples that they like to highlight is using deep neural networks to identify for object and image recognition, image processing. So some of the examples of things you can do, one layer might do nothing but identifying pixels of light and dark. Then another layer might refine the information about further, be able to identify edges and simple shapes. A next layer can identify more complex things based on combinations of those simple light and dark patterns and shapes. And then finally, you add enough of the right kind of layers, and then the computer can start to learn, what we think of as more non-trivial concepts, but like recognizing faces or other non-trivial objects, right? And so, of course, this is a big topic for Google and some of the other big companies. Google has been developing custom hardware just to do this kind of things, where they can build hardware that outperforms general purpose systems by large factors. And so, so it's a big industry, big interest space, very hot topic. So that very interesting and promising. So so that's the quick high-level summary. Any questions kind of about the basics before jumping into the kind of the fun security privacy stuff? Okay, so yeah. So let's start to look at the dark side of machine learning. So one of the things some people kind of naively claim about machine learning mirrors some of the naive statements about a lot of technology and about it's all upside. For example, one of the things people have said is, well, algorithmic decisions tend to be fair because math is about equations and not about skin color. How can a equation be biased or something like that, right? And that's maybe true as far as it goes. But in practice, it doesn't quite work that way. So, and this has been demonstrated repeatedly in different experiences. For example, there was a bit of a scandal at some point about Google's algorithm, apparently accidentally learning to show prestigious job ads to men, but not to women. So apparently, Google's machine learning was literally guilty of gender bias, gender discrimination. Similarly, Flickr had an auto tagging feature. It would try to analyze images and say, what was that? What are in this figures? And it had somebody noticed that it had a propensity to misclassify black people as apes, which is, you can't, was not seen as okay, understandably, right? And of course, it's very likely that in each of these and in many other cases, these are, more or less mistakes. I'm sure, pretty sure nobody was intending to make these machine learning systems behave in this way, but it depends on the way a machine learning system behaves depends on how it operates and what kind of data you give it. So, and biases and all kinds of things can hide in there. So another example that's even more scary, I think, is law enforcement and governments are interested in using machine learning to, say, analyze crime and even forecast which people, in a neighborhood may be more likely to commit crimes and, should be watched more closely. So this is kind of the ultimate, kind of law enforcers, wet dream, shall we say. How many of you have seen Minority Report, the movie? Okay, good. The rest of you should see it. Because this is the kind of thing, so, where Tom Cruise plays a police officer in the future Department of Future Crime that tries to predict future crime. And this is what quite a few characters in law enforcement and government would really like to use machine learning for. Predict, it makes a prediction. It's an oracle. It's all powerful. You just ask it a question and it'll give you an answer, right? And so there's this temptation to use it for this kind of thing. But in reality, when this has tried, it has failed in spectacular ways and result in severe ethical and questions regarding to the bias. For example, so in Oakland they tried to do something like this, and it turned out that the machine learning system basically predicted that mostly black people neighborhoods are recommended for closer observation and stuff like that. When in reality, drug crime is everywhere. Police basically find it where they're looking for it, and there's a lot of evidence for that. And that this kind of building a model that learns from data that was produced by real people with real biases, deciding which neighborhoods they're patrolling to produce the data, right? And so naturally, that preserves the biases from, takes the biases from the real world embedded in the data sets that this comes from, and embodies the bias in the algorithm, basically. And so then the algorithm, the machine learning system, ends up being just as biased as the people who generated the data that went into it, right? So, this is this is one of the many things that can go wrong in this space. Another example was a site called findface.ru, right? So this was a service in Russia that wanted people to upload photographs of their faces, and it would try to quote revolutionize dating by analyzing your face to figure out who you would be most compatible with, and kind of match people based on their faces, right? In some way, right? So yeah, so maybe this is great or maybe not. And they, it so happened that, of course, this creates a whole lot of issues, bias issues and other things, but also obviously privacy issues and security issues. And the founders even, commented at some point, I think, when asked some relevant question, like, how private is your system? They said, well, if the Russian FSB were to get in touch, of course, we'd listen to any offers they had, right? And of course, if you're running a business in Russia and the FSB gets in contact with you, you probably don't not listen to offers they have, right? If you want to stay in business. And this is actually, I'm sure Russia is not the only country in the world where that applies. So you know, there are huge both security, bias, privacy, and generally ethical issues in many applications of machine learning. Here's some other cases where. So how many of you have used Uber? Yeah, pretty convenient, huh? Yeah. So. I have to admit I have too, so guilty as charged. So, but they've been caught doing some really interesting, slightly shady activities. Of course, they have very sophisticated algorithms to try to match drivers with passengers, try to optimize drivers so that they meet up with passengers close to their areas, minimize travel time, maximize profits, all of this kind of thing. So a lot of good stuff, but in using these algorithms, if you have the both the opportunity to control the way the algorithm gets used, what data goes into it, what optimization function you're learning on, you're optimizing, then there's all kinds of less savory things you can potentially do with it. And Uber, I'm sure, is not the only company that was caught engaging in these more, slightly more shady uses of machine learning. In this case, they had a program called Grayball that would supposedly trying to protect Uber drivers from attack. Like, so don't drive through this neighborhood or along this route because it's a dangerous part of the city, or so maybe that's arguably legitimate. But then it was later used to identify and dodge authorities. So in some countries, the authorities were trying to crack down on Uber, and Uber was caught actually using that to avoid their drivers, getting caught or getting noticed by authorities. Never go past that police station or whatever, that kind of thing. Maybe even worse, or just differently evil. They had an interesting fare equivocation program where the system would compute several routes, some longer, some shorter, different levels of optimality, but then they would show different prices to the driver and the customers. So they would show the driver's app would see a shorter route with a lower fare, because lower price because it's a shorter route. But then it would show the customers a longer route with a higher fare. They would charge the customer the higher fare, give the driver the lower fare, and keep the difference, right? So nice little added, bonus for Uber, basically, right? So. And so, this is basically, was seen as a huge transparency failure, a huge ethical issue. So, and then there's been research that shows that you can predict a lot of aspects of human behavior through simple data, basically public data, such as who and what you've liked on Facebook, right? So this is from a 2013 study of about 50,000, 60,000 participants with Facebook, with their patterns of Facebook likes, and it showed that 70 likes. About 70 likes were enough to outdo what a person's friends knew about a particular person. So with only 70 likes worth of data, the machine learning algorithm could, basically, arguably knew you better than your friends knew you. About 70, and with about 300 likes, the algorithm knows, arguably knows you better than your partner knows you, right? And so, what this means is, is arguable, but it's, certainly it was seen as surprising and a bit creepy to a lot of people, and it's certainly a big privacy issue. If based on very simple sounding public data like this, machine learning algorithms can basically, completely eliminate our privacy in terms of our habits and behavior, then that's a potentially big issue. And of course, this type of thing has gotten in the spotlight again very recently. This has kind of been a burning scandal, burning issue for a while, and that just recently became a bigger scandal as Cambridge Analytica, a UK startup focusing on what they call behavioral micro-targeting, being able to use big data to identify individual people and figure out what kind of ad could influence them in the best way, in a very fine-grained fashion. And so they were being used in a lot of elections around the world by politicians trying to influence people to vote their way. And of course, there's still a lot of questions. How much did they actually succeed? They were used by Donald Trump's campaign. That was one of those over 200. And of course, the debates are currently raging as far as, how much did they actually succeed? What are the implications of what they did? How can people protect themselves, and what kind of responsibility did Facebook have? So the data they got to do this came from Facebook. In particular, they created a Facebook app called "This Is Your Digital Life" that was used to supposedly voluntarily gather survey results from a bunch of people. And so, they justified this on the basis that this is opt-in. The people who are participating in this survey are opting in to provide their data. But it turned out that the app, was not only gathering data about those particular people who had opted in, but all of the extended people in their extended friends networks too, right? And so when you bring in a kind of everybody in all those friends networks, that's of course a much huger set of data about a much huger set of people, and that's one of the things that has led to the current uproar about what they did. Of course, as well as the discussion of did this actually swing a major election? So, a continuing, ongoing question. So, so in summary, machine learning is, obviously a powerful tool. It seems to work really well for making predictions in a lot of cases, in a lot of applications. But it also, with great power comes great responsibility, yet again. So it can encode and reinforce discrimination depending on what data you feed it and what biases are in that data, even if the bias is only implicitly present, even if nobody is trying to bias the data. It should go without saying that it needs to be treated extremely carefully, especially when the data is used in ways that affect humans. That if it's deciding things about people's lives, what jobs they can get, whether they get more closely monitored by the police, or things like that. There's some very tricky, problematic issues. Okay. So, any question about that section so far? Okay. Actually, since this is actually a good time, let's take the break 5 minutes early and come back at 4:10.